All right. Yeah, Blaine, whenever you're ready.
All right. Welcome to Paleo Talks. We are at episode 17, and today we have Dr. Alex Hastings with us. Alex, there he is. He's always got that smile. And I was reminded and reprimanded for the fact that this is actually our first snake representation. It's shameful, I know.
Better late than never.
Both David and Alex have noted that to me. Yeah, we're episode 17. We'll have to have a string of snakes after this point, I guess.
Yep. All
sounds good to me.
Here on out.
All right. Well,
that's it. Paleo Talks, just the snake show from now on.
Paleo snakes. So again, welcome everybody. Alex is coming to us from Minnesota, and before we get too far into this, I do like to hand it over to David for just a minute, our science communicator who lets everybody know how the show works. David?
Yep, so this is going to be the same format that we usually do. So as a reminder, we're going to start off introducing our guest, letting Alex go through the presentation with Blaine prompting and asking questions. And then about halfway through, so 25 minutes in or so, we're going to let the audience know that it's time to take questions. So if you are here watching on Facebook, you can at that time leave your comments, leave your questions in the comments below or next to the video. If you're watching us elsewhere or you for some reason can't leave comments on the Facebook, feel free to go over to the Gray Fossil site, Twitter or Instagram. I'll be checking those in case we get any stray comments over there. And then the latter portion of the show will just be reading audience questions to Alex and getting as many answers as we can.
All right. Thank you, David. Just a reminder, we're coming to you from East Tennessee State University, Johnson City, Tennessee. We are the Center of Excellence in Paleontology, which also oversees the Gray Fossil site. And as always, when we talk about some of these other localities, I like to remind people that the Gray Fossil site is about 5 million years old. And Alex today is going to be talking about things that are much, much older. And so as he comes up to talk about some of those, we can sort of remind the comparison of those different ages. So Alex, having you now on the show, first, I want you just to tell us a little bit about your background, how you got into paleontology in the first place.
Yeah, so I was like your typical 3-year-old that just super geeked out about dinosaurs. I had family around the Smithsonian, so we'd go to the big dinosaur hall there. And it took till like the 10th visit to DC before we were actually allowed to see anything other than the dinosaur hall. Because it's just like, this is the best thing in the world. Why would you go anywhere else? So I don't actually remember, I don't have memory from a time when I didn't want to be a paleontologist. I'll say alongside that, I've just always loved reptiles. So now I get to bring in paleontology and reptiles together, and it's a beautiful thing. I did undergrad at Penn State and grad school at the University of Florida, which is home of the Gators. So that's about the best place in the world for me. So that was awesome. I did a research fellowship in Germany, which we're going to hit on here too. And I have been here as the curator for paleontology at the Science Museum in Minnesota for about 2 years now, which has been good.
And you're the Fitzpatrick Chair of Paleontology. What exactly does that mean?
So that means that there was a very nice donor by the name of Fitzpatrick that basically it's a partly endowed position. So that means that basically has got a little bit of financial security, which is really nice in case of times of budgets and whatnot. So, but essentially it's a curator position in charge of the paleontology department here at the Science Museum.
All right. Well, if you could go ahead and share your screen and dive right in.
Yeah, let's do exactly that. Yeah, let's go right there. Okay. All right. So title summarizes things pretty good here. So really back it up. Basically the kind of story of reptiles goes back more than 300 million years. And it's from kind of these unseeming little things like Petrolacosaurus here that we actually get the wide diversity of things that we traditionally think of as reptiles like turtles, alligators, lizards, snakes. but also dinosaurs, and honestly from there birds, which complicates what is a reptile, but don't worry about that. So this is going to highlight a couple of the cool things, but just know that there's a hugely massive rich history of fossil reptiles for hundreds of millions of years, and it's one of the things that makes them awesome. One of the reasons why I really like focusing on reptiles in terms of just kind of understanding kind of broader systems is because they are quote cold-blooded, right? So ectothermic is essentially the same idea there. It's your cool vocab word of the day. And because that fundamental need for temperature from their surrounding environment means that they are in a lot of ways more connected to changes in climate throughout their evolutionary history. So that makes them a really great group to better understand the relationships between life and climate through time. And this is where I think fossil reptiles can really contribute something to our greater understanding. So I wanted to kind of walk a bit through the work that I was doing specifically in Germany, and that takes you back to a time called the Eocene, which is the part where we're at is between 47 and 42.5 million years ago. And during this time, what you're looking at there is a temperature curve here. Basically, the main takeaway is that temperature is much warmer than it is today, like a lot warmer, even with our current climate. And since you get a very different set of circumstances there, especially with respect to these cold-blooded animals, you see some really, really fascinating things happening with reptiles. So I was working specifically in a place called the Geisel Valley, or Geiseltal, if you're speaking as German. And when you look at Europe at the time, it would have been basically a warm set of islands. So what you're looking at is the green is land, all the blue is sea, and where this fossil site is would have been definitely land, but the ocean wouldn't have been that far away. I wouldn't call it coastal, but I would say it's, you know, if you hiked out for like a mile or two, you would run into some seawater. And just really, really nice warm environment that it's just great for reptiles. The site is coal mine, essentially, and they're getting just ridiculous preservation. So like you've got this fossil frog here with all the little tiny bones in its body laid out exactly as they were in life, just unbelievable preservation across the whole ecosystem. They're even getting fossil insects, stomach contents of fossil horses. It's just ridiculously good preservation, all from this kind of window of time during the Eocene. Now, where I was coming into it was largely looking at the crocodile fauna there. So there are 4 species that definitely lived at the same time. So we had pretty good stratigraphic constraint, or kind of within the rock record. So we know that these would have been within a very, very narrow window of time, geologically speaking. So we have every reason to think that these things completely overlapped. When you look at modern ecosystems, we usually only get 2 different species of crocodilians. And where you do get overlap between those, they tend to be kind of different from each other. So like we've got a picture here of a modern crocodile, a modern caiman. These do overlap in northern South America. And basically, you've got big size differences where the crocodiles are much bigger than the caimans. These are both about year-old individuals. And they also tend to do a bit of different things diet-wise. They tend to live in the crocodiles live in bigger, more open waters, while the caiman are more upstream. So they find ways to kind of partition what they do within that. And that's just with 2 species living together. If you push it to 4, what does that do to the ecosystem? And are some of these crocodiles doing things that no living crocodile does, which is...
So Alex, when we look at them today, are there actually places where you can get 4?
So if you really look at it, there are places where you can get 4 caiman do technically overlap. I don't know that they live in specifically the same environment though, because they do tend to kind of partition each other. And I haven't been able to find any like good confirmed record of a person who went out, stood in a spot and said, all right, there's 1, 2, 3, and 4. I've never been able to find that record if it exists anywhere.
Is this in the Amazon region?
Yeah, exactly. In Central South America is where you get kind of a lot of different caiman species kind of nearish each other, and then there's a little bit of a spot in particularly like Western Brazil where you hypothetically could get interactions between 4, but from what I understand, it's not common by any means. So when you're looking at the kinds of crocodiles that we have in this German site, in the interest of time, we'll go straight to this really interesting one that stands out from the others. So you've got a couple that are all have kind of modern counterparts. There's one that's like a big crocodile, one that's more like a smaller alligator. But this one, Boverasuchus, has not only kind of a boxier skull, but it has serrated teeth. And that's front to back, all of the teeth are serrated. Now, when we look at serrations in reptiles today, they're very rare. No crocodile has them. But one of the things that does is the Komodo dragon, which is really cool. It's a big, giant land predator, right? It doesn't really do much of its hunting in the water. And having those serrations in the teeth is a really big advantage in that scenario because they've got to do this, right? So they got to tend to go for large prey that they then have to carve off pieces of, right? So those serrations are a really good advantage, particularly when you're on land and not in the water. So crocodiles, when they're in the water, they have the full advantage of being able to position their prey in more or less 3-dimensional space. So it's kind of floating there. They can come at it from whatever angle they need to, and they can bite repeatedly to break off pieces. On land, that's a lot more difficult. And we see serrations seem to be an advantage in that kind of habitat. But in order to kind of get a better sense of what that really means quantitatively, we can actually look at the way that the skulls are shaped. So when you look at crocodiles, the shape of the skull allows for certain kinds of prey to be favored, more or less. So something like a wider skull gives you a lot more strength and rigidity, and you can enact a lot more force without damaging the skull. So that allows you to eat harder foods. So like we've got a crocodile up top, and we've got a gharial skull, which is this weird long-snouted crocodile that's native to India. And it has kind of a long, narrow snout with lots and lots of pointy teeth that's really good at catching things like fish, but it's not great at enacting a lot of force. So that means that you can be specialized a bit to certain kinds of things or take advantage of different sorts of foods. So the idea being that if you were to see these crocodiles in Germany going after different things, we should see some noticeable and measurable differences in shape of the skull. So to basically summarize the idea of geometric morphometrics is just shape analysis. So you're taking different points on skulls, comparing them across both modern ones and fossil ones to basically quantify that shape. So you can then say this shape is more similar to this shape in ways that you can actually attach numbers to and get some statistics. Boil down basically a year's worth of work to this one diagram here is what you're looking at are the 4 species of crocodiles here, generalized or an average shape of the skull. And then by comparing that to the modern crocodiles and their diets, cross-referencing to the kinds of foods that would have been available to them at the time, basically worked out a range of the kinds of foods that you would expect them to go from for things that they would eat often to things that they would eat less often. And what you'll notice is Asiatasuchus here is very crocodile-like, so these are the same kinds of things you might see a Nile crocodile go for. Diplocynodon is very alligator-like. It's also small-bodied, so that's why there's things like insects in here as well. Alagnathasuchus on the bottom, going for really shelly stuff like snails and clams, which are also found there. But things get really fun with Boverasuchus. Now, when you're looking at the skull shape of this crocodile, it was most similar in terms of living crocodiles with the Cuban crocodile. Now, this is a lesser known crocodile, mostly because it's very, very rare. It's critically endangered, only lives in just a couple places in Cuba. But what we do know about its kind of biology or its kind of behavior is that it tends to go for land prey more so than other crocodiles. One of its favorite foods is the hutia, which is a large rodent. It's kind of like a small dog, large cat size. And there are lots of kind of these little anecdotal but stories of people seeing these things miles from any water source and even jumping from land up towards the trees to try and catch prey. So of the modern crocodiles, they seem to be a lot more terrestrial. And it's thought that they, even though they don't have serrations in their teeth, that this kind of exaggerated S curve to their jawline creates a little bit more shear, so that allows them to get through pieces a little bit easier. We see that to a certain extent in the fossil crocodile, though it's admittedly a bit squished, so that's a little harder to see.
Alex, in the Cuban crocodile, do you also get some lateral compression there on the teeth? Or are they conical like other crocs?
On the teeth, yes, they are very laterally compressed. So they're, which honestly makes them look like dinosaur teeth in a lot of ways, really. Which of course, another large predator on land. Yeah, they're fun. So when you're looking across the environment here for something that's similar, most similar to something like the hutia, both in terms of size, but also in terms of ecology and the kinds of habitats that we've been living in, the most similar thing is actually Propaleotherium and a couple other closely related species, which is a very early ancestor to the horse. So this is in the direct evolutionary line towards horses very early on. They're about the size of, again, like a small / medium-sized dog. And they would have been living in this pretty densely vegetated area. And of course, like anything, would need to go to water sources pretty regularly. So these things were actually fairly abundant as well. They're the most common mammal from the site, and we had a very, very good fossil record of these things around. But what about other kinds of things that might tell you what this animal was doing? So far, I've really only talked about stuff in the head. What about the rest of the body? Well, this is where just the abundance of riches at this site, because not only do we have great skull material, we have the rest of the whole dang thing. This is an unbelievably complete skeleton of Boverasuchus here. So we got the skull laying with its back of its head, or top of its head facing backwards. Got one arm here, another arm on top of itself, back leg, tail wrapped around. Even have stomach stones preserved right in the place where its stomach would be. And if you kind of simplify that a bit here, you got your outline. All the oranges are the bones that are preserved. So there's just a couple little things in like the feet and the ribs and a couple vertebrae that are missing. So this is unbelievably complete. You rarely get this kind of preservation. So from that, we can tell a lot of things. And there are some other partial skeletons out there too that can give us, to corroborate some of this. One of the things that you notice first and foremost is just that the legs are a lot longer. They're also would have been held closer to the center of the body because the pelvis is actually shaped a bit different. So it would push that kind of inwards a little. That would help especially because when you're moving on land, look at something like this big old gator here. They're a little ungainly. They can do the high walk. They can get their belly off the ground, but they're dragging their tail. And that's because there's tons of muscle in that tail to push it forward in the water. But on land, it's basically in the way more than anything. This crocodile, however, from Germany, had a much lighter tail. So it wouldn't have been nearly as muscular, would have been as actually even shorter. And on top of that, those kind of armor plates that you see like on the back of gators here are actually kind of thin and spindly and would have actually helped brace the tail even. So not only would it have been very light, but it also probably would have been propped up to a certain extent so that it would more or less keep itself off the ground while it was moving on land, which is really, really neat. The last thing that they had that really seemed to indicate that they're pushing towards land is when you look at the toes. So toes are actually very blunt and rounded. They're not sharp and pointy like modern crocodiles' toes. And as you can imagine, if you're kind of pushing off the ground, trying to move to catch something on land, that's going to create kind of a problem there. So they have what's often referred to as hoof-shaped toe bones. They're really not hoofs per se, but they're definitely modified to be much blunter and also much flatter on the bottom, which is also super, super cool. So basically, this is all kind of getting stitched together to this scenario where you've got something that by pretty much all the accounts that we can come up with, short of finding stomach remains, that these things were hunting down the early horses. So Boverasuchus, horse hunting crocodile from Germany, which is really cool and definitely something that we don't have in the world today. We got kind of some ideas of that with the Cuban crocodiles, but something much more terrestrially adapted and seems to have been well adapted specifically to early horses. So because I wanted to jam in two different ideas here, we are going to take our brain further back in time. We're also going to go from Europe to South America to Colombia in northern South America and take a step back to the Paleocene. So this is about 58 to 60 million years ago. This is still after the age of the dinosaurs, but it's relatively soon after, right? So mass extinction happened. Life is in this kind of recovery phase, and what you start to see is reptiles are taking advantage of kind of all these kind of ecological space that's available. And because of this area being the tropics, it's traditionally been really, really difficult to work in. So basically everything we found was new. So we were working in a coal mine and finding things like crocodiles. This is where I came in. I got to name 3 new species of these crocodile relatives called Dirasaurids. The picture on the right here is this long snout form that typically see. So we had one form with a long narrow snout that fit that well, but then these other 2 that didn't. So it was really pushing into new territory for the family. But of these 3, the one that impressed me the most was Anthracasuchus. This is the name I picked out. So we've got a modern gator skull here. We've got the fossil skull here. This is a snout. One of the things that you notice about this animal is that it has enormous area for muscle attachments to close the lower jaw, like much, much bigger area for muscles than we see in any modern crocodile or really across fossil crocodiles. Because this, as it turned out, was also matched with places for muscles in the lower jaw. So what we're looking at is something that had an insanely powerful bite. And we've got eyes and nostrils highlighted here. For the nerds in the audience that might have noticed the species name here, you might have caught this reference. So this is after the Balrog from J.R.R. Tolkien's Fellowship of the Ring, a beast that was unearthed deep in a mine, much like this fossil crocodile was a beast of flame and power. I'm a nerd, and my PhD advisor was okay with it. So that's officially in the fossil literature now. In terms of what it was actually eating, so you got these really big, powerful jaws. When you look at the teeth there, they're very blunt and peg-like. You can imagine if you had sharp, pointy teeth and you ram it against a solid object that's just going to shatter on impact. You want something that's a lot more robust in order to eat hard foods. And that's the kind of teeth that we're seeing in this crocodile Anthracasuchus. When you look at the turtles from the same site, you actually see bite marks that match up really well with those teeth, including a really, really big one that had about a 5.5-foot diameter. And we're still finding tooth marks even in the middle of the shell of that turtle. So that gives you a little bit of sense of not only the size, but also the strength to have enough force behind it to leave mark and solid bone in the middle of that shell. So that's at the edge of the jawline. So that's impressive. But bearing the lead here, right? We're supposed to have snakes. This right here is one of the very first pictures of a fossil snake from this site in South America. Now, little bit of background, biggest snakes that we have alive today are, of course, the anaconda, which is the biggest on mass, and the reticulated python, which is the biggest on length. Now, what I've got right here is an anaconda vertebra. I'm going to put up that same snake vertebra to scale, just to give you a little bit of sense of just how much bigger this fossil snake was. It's many, many times bigger, right? So your first question that anyone is going to ask is, how big is it? As it turns out, that's an enormously complicated question to answer, because it really matters where in the body that vertebra came from. We actually had dozens and dozens of these things. So we had to figure out where they came from, so then we could figure out how big the whole snake was. So we actually used that same shape analysis I was talking about with the crocodiles, where you match point to point to point across modern snakes from head to tail, and then across all the fossil ones to then figure out where this came from. This is largely developed with Jason Head and David Polly here. And from that, we're able to actually figure that out. Without further ado, we're looking at a snake that was about 43 feet long. So that's actually longer than your standard school bus is at 40, and would have weighed 2,500 pounds or 1¼ tons. That is a truly massive snake, much, much bigger than anything anyone had ever known existed. Would have been a close relative of the anacondas. This would have been a constrictor style snake, which partly accounts for the massive mass. It was a new genus and species. We named it Titanoboa serhonensis. Felt like a good name for it, Serhon coal mine, and it's titanic relative of the boas. Super excited, submitted this to Nature. We're like, all right, we got the biggest snake ever. We figured out this system. Rejected. That was not good enough for the journal Nature. But we did not give up. So we went back to the drawing board a bit and considered, how did Titanoboa get so big? Thinking about its environment and linking it back to things being cold-blooded or ectothermic. As it turns out, basically you can boil this down to a mathematical relationship between how big a snake can be and how hot its environment has to be just to keep it alive. From that, we're able to work out that the tropics were several degrees warmer than they are today. Now, this was especially important because at the time in particular, we were toying with this idea with future climate models that the tropics would stay relatively buffered, that they would not feel temperature change nearly as much as other parts of the world. This countered that and said that the tropics can absolutely get hotter than they are today, and that's going to dramatically affect the kinds of animals that do well in that environment. And that is how you get a Nature paper in the end. So this, I got super spoiled because this is actually my first publication. Sorry guys, it doesn't normally happen, but it was great.
Alex, I want to jump in for just a minute and let you know that there are 5 minutes left for the presentation part.
No problem. And we are almost
to go ahead and start making sure you're sending in questions.
Yep, please do. Yep, so just wind it down here. So as you can imagine, people do like big snakes. So we developed a traveling exhibit with the Smithsonian. I'm on documentary number 4 now, tied in with this, which is a lot of fun. It was also really neat as a grad student to walk into a Best Buy and see a DVD of your documentary next to a Betty White. I'll never understand why. I don't know why. I never will, but that's all right. I am very happy to say that the life model of Titanoboa is actually currently here in Minnesota. So if any of you guys will be around St. Paul anytime, this will be its home for at least a good long while. So we encourage you guys, we are reopening our doors in the beginning of September. So we hope you guys can come and check out the life-size model of Titanoboa. It's eating a crocodile, which makes me both happy and sad at the same time, but that's all good. Few acknowledgements, thanks to some funding sources, which is all very cool and awesome. And thanks to you guys for listening. In case any of you guys are in the social medias, I am at Dr_Crocodigator. And with quarantine, there's been a lot of just tweeting fossil-related toys lately, but happy to say I've been able to get back in the museum to do some actual fossil stuff and fieldwork too. So feel free to follow along. And with that, I think we've got some time for questions. I'll turn it over to you, Blaine.
Yes, we have quite a lot of time for questions, and David will chime in here in just a minute to start that. But one of the stories I want you to tell is I remember going to the Florida Museum to do some research, and we were able to see some of that Titanoboa material before it was published. So we heard about it before it was published. But I'd like you to tell a story about how you became involved in that research.
Sure. So I had gotten to the University of Florida, and my advisor, Dr. Jonathan Block, had been down to, I think he'd been to Colombia 1 or 2 times before that. So he had kind of gotten involved in a project. He was really hoping to find fossil mammals in this coal mine in South America, because really we didn't know anything from this time period from this part of the world. It's just a blank spot on the timeline and on the map. Basically the mine workers had started finding some fossil crocodiles as well as turtles and leaves. So that was enough to kind of get a few of the feelers out there, and eventually kind of word got around. And as a new grad student, I knew, we knew there were some crocodiles there. We knew it was all unexplored. So I was super excited to learn more about that. So that became my project. Edwin Cadena took on the turtles from the site that were discovered pretty early on as well. So basically it was us 2 grad students had started the field work there. There was a point where Edwin had done a bunch of collecting. He kept all the turtles down in Colombia where he was at the time, but sent a big old box of stuff that he thought was crocodile up to me in Florida so I could work on it at the museum. And the story goes, late one night, basically everyone, all the, professors had gone home for the night and that sort of thing. And me and just one other guy who was a grad student at the time, Jason Bork, were the only ones there. And I was just unpacking this stuff, seeing what we had gotten shipped up. And it was pretty clear pretty early on that there were some bones that were very, very much not crocodile in the mix there. So since Jason was there, I was just like, hey, come on over, check out this stuff that we've got here. After just a brief moment, I'll confess Jason was the first to make the connection that what we had here was not only snake, but it was like just insanely huge. And I remember thinking, even before my brain had clicked on that, I was like, well, it looks kind of like a mosasaur, but what the heck would a mosasaur be doing in the Paleocene in this land? That doesn't make sense. But like mosasaurs actually are pretty closely related to snakes. They have kind of similar vertebrae there, so that's why. But that's just like where the size proportions are. And then when you're used to seeing like little tiny snake bones and you see something this giant, like fist size, you're like, what the heck? So for one night, me and Jason were the only people in the world who knew about this thing. We were super, super excited. I remember Blaine knows Kenny Crisco, who is in charge of the modern reptile collection at the time at the Florida Museum of Natural History. We knew he would get in just like stupid early. Like he would be at the office by 5 a.m. routinely. So since we knew this, we're like, all right, we know we're not going to get in tonight, but we're going to be there. So we get in super early. Of course, Kenny was there at 5:01 or whatever. And we're like, oh my God, we need the biggest snakes you can possibly get. Give us anacondas, pythons, whatever you got. We pull out like all these things and we find like this beautiful 17-foot female anaconda skeleton, and the bones, actually, it was actually the one in this presentation, are just tiny compared to this giant fossil. So then we go excitedly at a more normal hour when John got in at like 8-ish something, and we're like, oh my God. And I remember John actually fought us for like 2 days, being like, that kid, no, there's no way. Finally, we convinced him enough to bring this to Jason Head's attention, and Jason just goes like, all right, I'm gonna go buy a plane ticket now to Florida to go see this. So Jason, I should say Jason Head is like the world's authority, especially at and at that time on fossil snakes. So this is very much his jam. And he ended up becoming the lead author on the project because he had a lot to bring to the table for that. So
well, thanks so much, Alex, for sharing the details of that story. Love it. We'll let David jump in with some other questions.
Sure thing. Yeah, we've got questions coming in from the audience. So before I start reading them, a reminder, if you're watching us on Facebook, you can start asking your questions in the comments, or if you can't leave comments on Facebook for whatever reason, you can go over to the Gray Fossil Site Twitter or Instagram and send us comments or questions there. I'm going to start off. We got a whole bunch of croc questions.
yeah.
So let's start. This is a question from the daughter of Carrie, who is almost 11,
Oh.
who asks, how fast did these ancient crocs move?
Ooh, I wish I could give you actual numbers for that. Short end is don't have great numbers on exactly how fast they would have been moving. I will say, in terms of swimming, modern crocodiles actually likely had a bit of an advantage because there have been a lot of these great adaptations for moving through the water. So one of the big ones is that the tail in modern crocodiles is really the only thing that moves, and it's just this powerhouse that launches the whole rest of the body forward. In these crocodiles, this is kind of a side branch to the crocodiles that we have today. They didn't quite have a lot of that adaptation. Instead, they would have had a much more kind of serpentine motion where they would have been going like this. So that would have likely not been quite as forceful in the end. So they're probably actually not quite as fast as modern crocodiles, but there were no modern crocodiles, obviously, so they didn't have competitors in that sense. So I'd say just a little bit slower than modern crocs, but still fast enough to catch dinner. So that's all right.
It looks like oh, go ahead, David.
I was going to say, oh, did you have a question you wanted to ask?
Well, I noticed there were a couple that had come in on bite force. If you could address whether or not bite force has been calculated on these extinct taxa.
Right. So I've been trying to get numbers on this because we know the muscle area is much, much larger for this extinct crocodile. Basically, you can use, there are ways you can calculate this out. It's largely based on size. A lot of measurements have been taken on modern crocodiles. If you do that, you get kind of something that's along the lines of modern crocodiles. But the problem is, like, because the musculature is so different from what we see today, that doesn't really give you a very accurate description there. I've tried to do basically it's going to be a massive like biomechanical study that I have not been able to get into. But you basically have to think about it in a very similar way to how they address this in honestly, Tyrannosaurus Rex. So basically looking at kind of muscle attachments and then force of muscles, and it's a much, much bigger, more complicated kind of thing. But just, I put at least some very rough numbers on it. And we're basically looking at kind of similar levels to, it was just a little bit less powerful than T-Rex and much, much more powerful than any modern crocodile.
And so, which taxon are you talking about?
The Balrog and Thracasuchus.
Okay. What about Boverasuchus?
Boverasuchus probably actually wouldn't have been, so short end is, again, musculature there is very different from modern crocodiles. It's not in the sense that it's just overpowered like in Thracasuchus, but because the skull is shaped very differently, we can't really very adequately apply those same models there, and there's not really good comparison. So again, you basically just got to construct it from the ground up. So again, we don't really have great numbers on there. Probably not overwhelmingly powerful in that sense, because it would have been something a little bit more in line with like a Komodo dragon or something that is not necessarily catching its prey with a powerful bite like a modern crocodile, but kind of being a little bit more strategic about things. There's a whole aspect to Komodo dragons that is called persistence predation, where basically they wound their prey and then they just kind of follow them until they die. Whether or not this crocodile did that, we can't begin to say, but it's a possibility. But in any case, it wouldn't have had an insanely powerful bite, more than likely.
We got a question back on Boverasuchus from Aaron, who says, you said that there are multiple ages of Boverasuchus represented. Do you have really young individuals? And what do you know about the ontogenetic changes that take place in the skeleton?
So we have the youngest ones would probably still be about like 5 years old or something like that. So they're not super young. From that, we do see a little bit of shape change in the skull a bit there. So we go, basically it gets seen, or at least seems to get a little bit kind of boxier as you go from hatchling. But again, this is kind of a trajectory that's going from kind of a midpoint to an endpoint and not the beginning to the endpoint there. The really nice big skeleton there seems to be about the upper bound for body size there, which is about 2 meters or about 6 feet-ish in length, which is still big enough that that puts, you know, the small horses of its day pretty comfortably within prey size.
All right, we've got another question. Greg McDonald asks,
Yeah.
do you have any croc coprolites from any of these croc sites? So fossil poop.
Yes, so there are coprolites from actually both sites. And from the German site, basically we don't necessarily know that any of them are from Boverasuchus specifically. So they're not, typically aren't found right next to the animal when it died, unfortunately. So these could come from one of the other species there. And from South America, we actually do have one that was found directly with a skeleton of one of these Anthracosuchus. It was actually kind of a bit small though, which makes me a little bit hesitant to say that that's what it came from. The nature of the site from South America though, they are a lot of the internal structure of things is lost. So we don't tend to see like spongy bone inside, like it's all been fully infilled and mineralized to the point that you can't really distinguish things. So in terms of like getting content out of the coprolites, it's not looking super promising, but we're definitely going to put at least one of them through just to see what we can find.
Alex, we have one from Will Jelnaw, and he notes that there are a lot of Boverasuchus specimens that are identified here in North America, and wondering whether or not those are the same taxon and if there's any good skull material here that also represents that same taxon.
Right. So this is a genus that's been known as Pristicampsis for much longer. Basically, what you're looking at is what was regarded as kind of distinct North American taxa for a long time until revision by Dr. Chris Brochu out of Iowa basically found basically taking a old name from one of the older German publications, then is now applying that to ones that show up particularly around like Texas, but there's a few other places. There is some decently complete material. I haven't gotten to spend a lot of time with it, but I do know that a lot of the same features that we see in Europe, we also see in North America. So you get the kind of tall skull, the serrations in the teeth, the compression in the teeth, and I believe there is some parts of the skeleton as well that are also indicating some of these kind of terrestrial adaptations. So it's nothing as complete as that really nice, beautiful skeleton in Germany, but still a good bit. And it would have been here in North America, or a very close relative would have been here in North America too.
We've got another question from Carrie's daughter, who asks, how many years of school have you had?
All right, so if we're just counting college years, right? So there's 4 years of undergrad, not totally proud to say, but it was a 7-year PhD for me. So that's a long time. Some people, there's a range of this. So I would say kind of 4 to 6 is well, 4 is on the lowest side in America anyway. So I'd say like 5 or 6 years is pretty typical for a PhD. Some folks actually take even longer than 7 years. So it's a commitment, but you are learning really awesome, amazing, cool things, getting to do really fun stuff. So it was fun the whole way through, even though it was quite a while.
Yeah, I'll comment on that too. So overall college that I went to was 11 years.
Yep. Yeah.
Is that
So like a
what-
lot of people do a master's in between an undergrad and a PhD, especially, you doing completely different projects and all that sort of thing. So that typically when you add all that up, it tends to come out around that same place anyway. But
Yeah, it can be a lot of time in school, but hopefully all a good time in school.
yeah, definitely.
We've got a question from Dylan. So Dylan is referring to, asks, can you explain what appear to be stones underneath the belly of the complete specimen of Boverasuchus? Are they osteoderms?
No, they are actually stones. So they are what we call gastroliths, which literally just means stomach stone. This is something we see in modern crocodiles as well, and actually even like some kinds of birds and stuff. Basically, they will intentionally swallow stones in order to basically just aid digestion. So since they're not able to chew their food, they swallow big hunks of stuff. And then by having those stones in their stomach rolling around, that kind of breaks up the food a bit. So that way it kind of makes digestion a lot easier. And because this site is just ridiculous for preservation. We had, I think it was like 20 or 30 skeletons of different species of crocodiles from the site in Germany. And each one of them had this lovely little packet of stones right about where you'd expect the stomach to be. So there's actually a whole other project that's ongoing to actually figure out kind of the relationships of, size of crocodile to the size of the stones to the quantity and that sort of thing to actually figure that out in the fossil record, which will be really cool. So this seems to have been no exception for Boverasuchus, that it was also consuming these just to aid digestion a little bit.
Very cool. Yeah, I was wondering if that's what that was. And so there was a discussion has popped up in the comments about gastroliths.
Nice, yeah.
There is one other question that we've got here from Grant. Grant asks if there's any isotopic work that's been done on any of these crocs you talked about.
There's a tiny little bit has been done on the German site. There was actually a really cool study that was mostly focused on the bird from there, Gastornis. So there's this really, really large, 6-7 foot tall bird that lived there. And there are these open questions of a lot of people that interpret these things as being really carnivorous, but the morphology in comparison to modern birds wasn't really jiving with that well. So they did an isotopic study. The main takeaway from that was that they were indeed herbivorous, but in order to generate kind of meaningful comparisons for the environment there, they did get some isotopes of crocodiles from the site there as well. I believe they did both bone and teeth. So that's the only isotopic work that's been done for either of the sites. Fortunately for a lot of the stuff from the South American site, it's pretty affected chemically and other ways as well. So we have very, very little enamel on the teeth, which is usually where you want to be able to take your really good chemical samples. So it's not been super promising from the South American site. I'll say there's definitely lots of more potential from the German site, but that's the only thing that's been done so far.
I see that Aaron Woodruff also has another question about Boverasuchus, because you mentioned that there were different aged individuals and whether or not any kind of ontogenetic work has been done to look at changes over time.
Short end is not really. So I've got kind of this longer term plan to work through the entirety of the Boverasuchus material. Now that I'm not there, that's a little bit more difficult, but short end is the younger specimens are the most fragmentary, which kind of makes sense to a certain extent. So you're not going to get like a beautiful, wonderful ontogeny across the whole skeleton for this taxon, but there are definitely still bits and pieces that can be pulled out from that, particularly in the skull. Rest of the skull is not great.
And we're going to do our finish our alligator work before you do that project, right?
Yes, I am swearing here, recorded live on Facebook, that is the first and foremost thing that we'll get out there.
Several alligator projects that are underway.
Yes, those are priority one, yes.
So, Alex, it looks like we have answered all the questions from our audience.
Okay.
But I have a question that I'd like to ask, partially because we haven't talked enough about snakes, I think.
Good. All right.
You show, so I've seen, oh, and then there's Cat. You showed that reconstruction of Titanoboa with the croc in its mouth, which I've seen before, and it's a very cool reconstruction. I seem to remember seeing the suggestion in a paper not too long ago that Titanoboa may have focused on eating fish. And I'm wondering if you have any insights or updates on what we think Titanoboa was actually eating, if it was specialized in anything.
So the short end is I'm actually technically supposed to be pretty quiet about this. There's some upcoming work that will address that exact question that you're asking, and hint is that you are on the right track. Yes.
Okay. All right. You heard it here first, everybody.
Yeah, along the same question with David and continuing with snakes, are you guys finding, or did you find more Titanoboa material that would indicate different sizes?
Yeah, so we're at, I think, 150 individuals now. That ranges from some it's like one bone, but there's ones where we got, a few dozen vertebrae in a row, and we're seeing quite a good size range in terms of like anatomical details. Everything seems to be essentially the same thing, so just younger or smaller individuals. If anyone's familiar, so anacondas, there's really, really large size disparity between male and female. So that might explain some of it. So where females are much, much, much larger than males in full adult body size, as big as they're going to get. And there's actually a little bit of growth study that's been done as well. That's also upcoming work there. In any case, there is a size range for Titanoboa. I'd say the smallest ones that we've found so far are about that big versus the ones, the big ones that are out there. And that's for similar positions within the body. So more to come there.
Exciting.
Yeah.
Very cool.
All right. Well, if there aren't any more questions, anything else you want to add, Alex?
I hope you guys can come and see it for yourself when you're standing next to something that's, at life size. Like, one of my favorite things is that a lot of people have come in and been like, nah, like no, you guys blew it up or something. Like, no, this is like legit actual size. This is what actually existed here on Earth. So
Alex, what if your large Titanoboa is a male and you haven't found the females yet?
Then that'd be crazy. That'd be great. Hey, why not? Even bigger.
All right. Well, thanks again for being on the show, Alex. And just hold on for a minute, and David will stop the feed here. Thanks everybody for listening in.
Thanks for the questions. Thanks for joining.